Yes. It's the last day of the F-Theory workshop, and we will kick it off with Jim with a large title as well, not only a large ensemble.
All right. So I'm a little under the weather, as unfortunately many of you have probably had to hear for the last few days, and I apologize for that. Hopefully that means that I'll use fewer words and speak more slowly, which, given my history, is probably a good thing. I'd like to thank the organizers for inviting me to speak at this wonderful workshop. In talking with numerous participants, it seems that everyone just loves coming to Madrid. Things always go off without a hitch, and things are so well organized. So thank you very much for all the efforts. Today I'm going to tell you about some work that I've done with Cody Long, who is in green here because he's played such a central role on all of these works, and a number of other collaborators whose names you can read. And I'm going to tell you about a large ensemble of F-Theory geometries. One thing that I'm also going to tell you about that has come up in the last, I have a plot that came off the cluster yesterday, so I'm going to tell you about that, just because it's so cool, I'm going to tell you about the weak and the strong using some robots, some artificial intelligence agents, and this is very, very preliminary results, but it's just too cool not to show you guys. This is work with Cody and with Fabian Rula and with Jiahua Tian, my student, this is based on something in data science called reinforcement learning that Fabian and I have been thinking about with Brent Nelson for a while, and about 10 days ago we started applying it in a different context and are getting some really cool results. All right, so the outline, just a question that we're all interested in is, what does the F-Theory landscape look like? That is a question that is driving many of us. We're hearing many talks about the swampland, we're hearing many talks about the landscape, and what does it look like is an interesting and broad question. What I'm going to do is show you a large ensemble of F-Theory geometries, and I'll be very, very concrete. In an audience like this, I don't have to give tons of background information because you know so much F-Theory, which is great. And large here means a specific thing. It means so large that you can probably never, ever put this whole ensemble on a computer, which is a different sort of large. We run into large ensembles in that sense pretty regularly in string theory. And a natural question is, if you have something that can't ever really fit on a computer in its entirety, how do you deal with it? I'm also going to talk about universality of non-Higgsable clusters and also strong coupling. The conclusion will be that F-Theory is very F-theoretic. It's something that we all know, but I'll try to put some teeth on it. And I'll also talk about something called anomaly detection. This is not an anomaly in the sense that we mean it, usually. This is an anomaly in the sense that the rest of the world always means it, something that happens rarely. So if something happens rarely in a large data set, the question is, how do you detect it? Some of the universality things that I'll mention are also supported by evidence from data sets of Wadi Taylor and Yinan Wang. Okay, so this is our large ensemble of F-Theory geometries. We have sort of two ensembles of roughly the same size. Here is the large number for one of them. You can see that I'm sort of building up some objects that look kind of toric, and this is a very toric construction, and these are the sorts of pictures that mean something in this context. So how do we get our large ensemble? Similar to in Wadi's work, we're going to be talking about bases and transitions between bases and the corresponding Calabi-Yau elliptic vibrations over them. So our starting point is a weak phonotoric threefold base. Such a thing is described by a three-dimensional reflexive polytope that then has achieved a fine regular star triangulation. Here are two of the big facets that actually exist in three-dimensional reflexive polytopes, appropriately triangulated. These sorts of pictures will play a major role. The basic idea is to take that building point and build on top of it, that starting point and build on top of it. From sequences of toric blowups, you could take a little cone as represented by an edge and blow it up, and then continue blowing it up and study the possible sequences of blowups that you can get from a two-dimensional toric variety represented by a cone. One thing that's important is that there's two different types of blowups: curved blowups, which are edge blowups of a little edge in a fine regular star triangulation, and point or face blowups. So here's the language that we're going to use. There's a lot of combinatorics here, so we, at least in our group, found it useful to give some other language. So a sequence of blowups, because you have all of these exceptional divisors getting built above the polytope, we'll call that a tree. those exceptional divisors, if your sequence of exceptional divisors associated with the blowup is a tree, might be appropriately called a leaf. Trees over edges, we will call edge trees, and trees over faces, we will call face trees. So if we have this tree and leaf language, and we're building these blowups, these trees over these reflexive polytopes, you might ask, what should you call the points on the polytope? If you'd like, those are leaves on the ground, which you might also call roots. So this is the structure that we'll run into. So what we're going to do is that we're going to classify all trees with height less than or equal to 6. This is related to this so-called 4-6 condition that's related to canonical singularities being finite distance in moduli space, etc. This is sufficient for that condition, which means that we're going to be forming one big connected Calabi-Yau moduli space. So the way that we're going to do this is do so by exhaustively, and it really was exhausting, constructing all the toric blowups. So if you're wondering what this picture looks like, you might ask, what are all of the possible height less than or equal to 3 edge trees? Well, an edge tree starts with an edge on a reflexive polytope and then blows it up by adding that divisor, but then you could blow it up another way by adding that one or by adding that one, and finally, you could end up with this one. So there's this set of height less than or equal to 3 edge trees, and there's 5 of them. A face tree is going to be built on a triangle. Instead of subdividing edges, you subdivide triangles, and here are both, there's only 2, height less than or equal to 3 face trees. Now remember, the condition for us is height less than or equal to 6, but you might ask how, if you consider height less than or equal to n, for n between 3 and 6, how fast is this growing? The number of edge trees and the number of face trees are growing at different rates, but the number of face trees gets quite large. So once you have this notion of trees, which are little blowups that you can do locally in the toric variety, you might ask, can I stick lots of these trees together to form a forest? And you might imagine this is where the large numbers are starting to creep in, because if I have lots of possible different trees, and I can put those together in lots of different possible ways, I'm going to get lots of different possible geometries. So each tree is data representing a local sequence of blowups. You might say, okay, let's form a forest. That's a 3-fold base B from trees by systematically adding trees to a fine regular star triangulation of a 3D reflexive polytope. The way that we do it is face trees first, then edge trees, and then what you do is you count. So the polytopes whose triangulations have the largest number of faces and edges totally dominate the ensemble. There's 2 such polytopes that have 108 edges and 72 faces, and these are the very large facets of one and of the other. The basic point, and I should actually hold on to this picture for a moment, for example, there's 41 million height less than or equal to 6 face trees. And what that means is that when I'm adding trees, I can add to this little triangle 41 million different things. And to this little triangle, I can add 41 million different little things. And to each edge, I can add 82 things. So you just start multiplying and you get the combinatorics. And the numbers get very large. So there's 2 dominant polytopes. Like I said, there's 108 edges and 72 triangles on each when triangulated. And this gives rise to 2 different ensembles of order 10 to the 755. I like to emphasize the fact that we actually compute the coefficient. This is not order. This is an exact lower bound on the number of F-theory geometries. Okay. And also we studied network properties in this paper, which I'd like to advertise, but it's a little tangentially related to the talk, so I'm not going to go into the topological structure, the network of these geometries. Okay, so we have this really large ensemble, and you might want to ask things like, are there universal features in this ensemble or not? And that's what we'll talk about. The technique that we'll use, obviously, we do not put this extremely large ensemble on a computer. It would probably create a black hole and eat all of us up before we were able to do anything. What we're going to do instead is, because we have such a precise construction algorithm, we can systematically control certain aspects of the ensemble and use our knowledge of the construction algorithm to derive universal results. So the results are going to be about the likelihood of non-Higgsable clusters, high probability minimal geometric gauge groups, and that the Sen limit almost never exists. If you'd like, the F theory is F theoretic. So non-Higgsable 7-branes is something that has been studied by many people. Remember that the basic idea is that if you have some fixed base B, and you construct the most possible F and G that are general in a Weierstrass model over that base, sometimes you have overall factors. And what that means is that you'll get some 7-brane that is always on some particular divisor that you cannot get rid of via any complex structure deformation. If that 7-brane is carrying a geometric gauge group. What it means is that there's no complex structure deformation that can Higgs down to a lower group. And one thing to emphasize is that whether or not you have these is determined entirely by the topology of B. So if you have a large ensemble of bases, you can just ask about the collection of non-Higgsable clusters in it. And in particular, non-Higgsable 7-brane, I'll mean one such 7-brane, but generally you'll have many such 7-branes which give rise to what's called a non-Higgsable cluster. It's a network of intersecting non-Higgsable 7-branes. All right, so universality of non-Higgsable 7-branes. Consider an edge or a facet on one of these polytopes, and consider the possibility of forming a height 2 blowup on that edge or facet. What happens when you do this is that from the point of view of the sections that can exist, the monomials that can exist in F and G, this is giving an extra hyperplane constraint that is cutting out some of the sections and will generally increase the likelihood of non-Higgsable gauge groups. And what we found is that if you do a single height 2 blowup of this type, this cuts out a special monomial in F and G that forces type 2 non-Higgsable 7-branes on all of the corresponding divisors. I accidentally cut this off. All of the corresponding divisors interior to a facet. So for example, if you perform that blowup, you get at least type 2 non-Higgsable 7-branes on all of these red dots. Each dot is a divisor, and each one of these red dots is carrying at least a type 2. And because of this, you can say, this is a pretty simple condition. Can you compute the probability that this occurs? And in our two different large ensembles, the probability is very large. It's not exactly 1. We know of examples where it doesn't happen, but it's extremely close to 1. It's greater than or equal to 1 minus something like 10 to the minus 755. So this is showing you that at least in this ensemble, and this is supported in Wadi's ensemble too with Yunnan, non-Higgsable 7-branes are extremely generic. Universality of large gauge sectors. Those type 2 non-Higgsable 7-branes are not necessarily carrying gauge algebras, and they can get enhanced with high probability. So one thing that we found is that when you start random sampling from this ensemble, you very often find that all of the divisors associated with points on the polytope have some explicit, have some E8, will very generally have E8 gauge factors associated with them. So if I have a little triangle that I'm doing some blowups and the guys on the ground carry E8, what this theorem that we found tells you is that in this high probability situation where you have E8 on the roots, the gauge group and the Kodaira fiber are uniquely determined by this height of the tree. So this height condition, which tells you how high the exceptional divisor is above the polytope, is sufficient to determine the gauge group. And the reason that this is useful is because it lets us put a lower bound on the gauge group. The gauge group is greater than or equal to this very large gauge group, where HI is the number of height I leaves above E8 roots. And basically, this tells you that the rank of the gauge group is greater than or equal to 160, and it'll almost always be bigger. The probability, given the assumptions that we had that gave rise to this result, the probability is that this happens greater than or equal to 99.99995% of the time. We totally believe that there's going to be more general assumptions that one can show even stronger results, but these were the ones that we were able to prove in our first paper, and it's already telling you that you expect very large gauge groups. For those of us that like to think cosmologically too, it raises an interesting question of what do these mean cosmologically? Do you have dark glue balls that you should be thinking about if inflation is reheating some of these sectors? But that's just a side comment that to me is an interesting question in the presence of such large gauge groups. Pardon? Anomalies? Can you ask that after? Yeah, thanks. Cool. Good. So another thing that is true in this ensemble is that the Sens limit almost never exists. So remember that the Sens limit is a weakly coupled type limit in type 2. It's a weakly coupled type 2b limit in complex structure moduli space. And it doesn't exist if you ever have a non-Higgsable 7-brane with a fiber that's more singular than I0 star. What that means in simple language is that you can get F4, E6, E7, and E8 in F theory, and if you're ever in a situation where you have such a thing on a non-Higgsable 7-brane, it means that there's no limit in complex structure moduli space that can ever take you to weak coupling. And we found some simple conditions under which this occurs, these non-Higgsable 7-branes, that violate the Sen limit, and the probability of these simple assumptions related to certain height blowups, the details aren't critical, is that the probability that a Sen limit exists in this ensemble is less than or equal to 10 to the minus 391. So the conclusion, if you'd like, is that F theory is very F-theoretic, Weakly coupled type 2b, we like to ask the question, what is the lamppost effect and how severe is it? On the one hand, the great thing about weakly coupled type 2b is that we can compute all sorts of things that are harder to compute and control in F-theory. But on the other hand, there's a question of what percentage of F-theory really is weakly coupled type 2b. Yeah. So you might ask, can you better understand this 2b lamppost and its boundary? So these are all the things that I have to say with respect to universality, but namely that weak coupling almost never exists in this ensemble, and that non-Higgsable 7-branes and very large gauge groups are totally generic. So it's also interesting to ask the question, how do you study very rare things in the ensemble? How do you detect and understand rare phenomena in relation to a much larger ensemble? How do you detect anomalies? This is something that computer scientists are interested in. They like to, monitor network traffic for malicious activity, and they like to be able to distinguish normal activity, which is the vast amount of activity, from amateur hackers, some teenagers sitting in a room, from professional hackers. And they like ways to, based on network traffic, see how what is the likelihood that you're in one of these three categories. And of course, this is a very small number of people relative to these other cases, but one wants to find them and stop them. So there's a warm-up in this ensemble. There's a gauge group result that we found. This is a simple E6 puzzle that'll give you the flavor of what sorts of questions you might ask with anomaly detection. The gauge group result is that this ensemble is dominated by 4 particular gauge factors, E8, F4, G2, and SU2. You might ask, those don't look very standard model-like. Can you get an E6 or an SU3 in the game? And what we found is that in our first paper, we couldn't find a systematic way of understanding this. But we did find that when we random sampled, there was a probability about 1 in 1,000 or 1 in 2,000 that E6 arised on a distinguished vertex. That's this particular vertex. So you might ask, under what assumptions is it? What are the variables that are really controlling whether or not you have this anomaly, this thing that happens with probability like 1 over 1,000? And what we did was we tried to ask the question, can we train a machine learning model to accurately predict yes or no for whether E6 exists on this particular vertex? And if so, can you learn how the algorithm makes a decision? And if it makes its decision in a way that you can understand, can you turn it into a conjecture that you can then prove? The CS buzzword for this is intelligible artificial intelligence. So the point is that by using machine learning to generate conjectures, in some cases you might be able to take its numerical results and turn it into rigorous results. Okay, so this E6 example is not the main thing I want to show you, but basically just what we did, we used supervised machine learning. The basic idea of supervised machine learning is given a large number of input-output pairs, what you want to do is learn to predict the output given the input, and then once you have a model that has been trained in this way, to be able to test it on unseen data to see how well the model that you've trained does. The training data that we had was 10,000 random samples with no E6, 10,000 random samples with E6. The input was a particular large set of variables that seemed relevant, and the output was whether or not E6 existed on this vertex. So what we found is that the models worked very, very well with greater than 99% accuracy. Remember, 50% were yes and 50% were no. So it was able to determine whether it was yes or no with high accuracy. Excuse me. And so what we were able to do was generate a conjecture from this. The model basically showed that only 2 of the many variables that we studied matter, and that leads to a conjecture about what are really the discriminating variables that are determining whether or not you have this gauge group. We computed from the theorem an exact probability, and we took 2 million random samples 5 times. Given 2 million random samples, you expect there to be 1,182 such examples based on the theorem. And then when we went through and actually ran the random samples, we were finding things very consistent with this prediction. So this is a rigorous result from machine learning, and it's not, there's more interesting results in the world, but the basic point is that you can actually, in certain cases, take these numerical results and turn them into theorems that are useful. All right, this is the evaluation of the models. There's a whole bunch of different models that we tried. The best one was something called a logistic regression, and this is greater than 99% accuracy. This is the mean. Okay, so what I want to end with is something that's come up in the last 10 days that is pretty fun. This is my student Ben, who's great, and we basically, for these weak coupling results, what we did in our paper is you try to come up with assumptions that are very high probability and that are sufficient to force non-Higgsable clusters on you that obstruct the send limit. So the name of the game is, can you come up with high probability assumptions that lead to that happening? So the first theorem was pretty good, but it didn't make the paper because Cody came up with better assumptions that had higher probability that gave a much stronger result. So we came up with something that was, semi-clever and led to a nice result, but Cody blew us out of the water and he came up with a much better result. And so, of course, we didn't put this result in the paper. But a natural question is whether there's assumptions that show even more than we already did that type 2b is vanishingly small inside of this F-theory ensemble. So the goal is to not just study the probability, but to actually explore if you'd like, the weak coupling lamppost and probe its boundary. So what we want to do is we want to move around in bases that keep us at weak coupling, and then the second that we step out of bounds into a case that doesn't admit a send limit, we want to know what's happening. So this is going to use something called reinforcement learning. Supervised machine learning predicts, but reinforcement learning, sometimes people call this artificial intelligence, explores or searches. The most famous examples of these techniques, I put a question mark because that's totally subjective, is these are AlphaGo and AlphaZero. These are some of the most famous examples of reinforcement learning. These use basic ideas from behavioral psychology. It's a beautiful subject. It's actually relatively easy to understand, and compared to our field, they did a great job choosing their buzzwords because I can just tell you now and you'll understand it. So an agent is something, and everything in green is one of the buzzwords. An agent interacts in an environment. It perceives a state from state space. It has a policy function that picks and executes an action given the state. The agent then arrives in a new state and it receives a reward, and successive rewards accumulate into a return, and sometimes you choose to penalize future rewards because rewards now are better than rewards later via something called a discount factor. And the whole point of this setup is, this is kind of like Pavlov's dogs, is to basically have your policy get optimized over time in a way that maximizes the reward. So this is the name of the game. Colloquially, the simple way is that you just have this agent, this little robot that can explore a system, and it learns how to act in more and more intelligent ways. So the reason why this might be relevant for exploring weak coupling limits in our ensemble is that the geometries where a send limit might be possible are all connected to the initial case that we study, which is this fine regular star triangulation of this 3D reflexive polytope. And so we decided, let's try to set up a game that actually uses these ideas to try to probe the boundary of this lamppost, if you will. So the game is this. We start with some 3D reflexive polytope that's triangulated, and we start adding trees, moving away from it. The game, the boundary of this space is the boundary on the other side, no send limit is possible. Inside, a send limit may be possible, but outside it's definitely not possible. And the name of the game is just to move by placing trees and moving away from this case. The goal is to stay in bounds. We decided we'll give the agent 100 points if it stays in bounds. For every step that it takes and stays in bounds, it gets 100 points. And the game is over when it's out of bounds. So this is, there's still a lot to do, but I want to show some promising initial results. I have a slide on implementation, but I'll skip it in the interest of time. Basically, the upshot of this slide is that computer scientists do a really good job writing algorithms so that we don't have to, which is really nice, so that we can focus on what is the physics of the environment and then use their algorithms to make progress. The particular algorithm that we use is something called A3C. Okay. So if we have this game where this little robot is exploring the weakly coupled landscape, the first thing that you want to do is ask if it was doing the dumbest thing, which was just a random walk, randomly adding trees all over the place, what would you expect? So this agent, all of these plots, steps are going to be on this axis and scores are going to be on this axis. And remember, it gets 100 points for every step it takes and stays in bounds. So this is what we learned from this. The random walk, if you do it this way, you're getting 2 to 3 steps while staying in bounds. Before you go out of bounds. And in particular, on the subsequent slides, this is going to be very, very low. The scale is 200. The first try, this was the first plot that, I'm showing you this in time series just because it's fun to see how the results actually come out in real time. The first thing that we did was we just did 50 million steps, and we see that it actually learns very, very quickly. The random walk cases would be a straight line down here, and you can see that this agent learns very quickly and sort of asymptotes out at 4,500. That means that it's taking 45 steps before it hits a base where there's no send limit. But of course, this is not the way that you want to draw the plot. You want to have more data points in here, and you want to expand the asymptote out. So that's what we did, and you can see that it's really learning over time. But we see that it's sort of hanging out at 4,200 for a while. So can it do better? Well, this is 10 million steps. This is 10 million steps that this agent takes and learns in the process, but you can train it for longer. And what we did was we first of all did a tweak. We didn't increase the number of steps, but we used something called an LSTM neural net. And in this case, we see that it's not doing much better overall, but there's an interesting feature where there's 4 sharp plateaus here. So if you'd like, the agent is evolving as we go in time. The extent to which it has evolved and can take more and more steps without hitting a boundary is going up that direction. And there's 4 sharp plateaus. And this is something in biology that is called punctuated equilibrium. You may remember it from biology, from evolution. Species in certain cases stay the same for a while, but some event causes them to evolve rapidly. So we tried letting it go a little bit longer. So this is up to 20 million now, and you can see at some point some random fluctuation caused it to start learning again. And the 5th try, this is the best yet, this came off the cluster yesterday, is that now we are able to take over 100 steps, add over 100 trees while still being on a base that maintains the send limit. And the random walk would have been a flat line way down here at 200. So this is just training. This is not the point of this work. The point of this work is to take these trained agents and really learn something from them and have them do something. But I'm showing it to you because it's just cool, frankly, that these techniques allow something to learn how to explore space so well. Okay, so the conclusions, just to conclude, is that the number of geometries in the landscape is large, so large that you can probably never put it on a computer. Yeah. Those numbers that's definitely the case. And there's other ensembles that are similarly large. Non-Higgsable clusters, large geometric gauge groups and strong coupling are totally universal in the ensemble. This matches the results of Taylor and Wang. Anomaly detection is something else we looked into. Rare phenomena are also interesting. And I showed you that you can actually get rigorous results from machine learning if the details of the model allow you to generate a conjecture, figure out what the assumptions are that would actually lead to a theorem. And then we talked about exploring the type 2B lamppost. Reinforcement learning was used to evolve artificial intelligence agents. A random walk, you would only take 2 or 3 steps before you hit the boundary. But because this thing can learn over time, it now knows how to take 100 steps while sort of staying in bounds. So that's it, and thanks a lot.
Are there any questions? Small or large?
So the 6D problem is much easier, presumably, than this one. You're doing 4D?
Yeah. I'm doing it in 4D. You could also do the same thing in 6D and do 2-dimensional toric bases and run.
So that should be much easier for you to analyze and finish in some sense, right?
Yeah, that's right. I haven't looked into it yet, but it would be really interesting to do that. Okay. Yeah.
More questions? In the back? Jonathan.
First cough of the talk. I'm doing all right.
Can you comment on what you expect to happen if you put in, say, a non-trivial potential energy on? So here you're imagining the thing can just randomly move around because all the directions are kind of flat, right? Can you comment on what you expect to happen if there's a non-trivial potential energy?
Yeah, that's a really good question. So all of these agents are starting with a random walk, and they're changing their policy over time according to what rewards them, right? So what one would like to be able to do if one wanted to really mimic a cosmological situation, for example, which is presumably what you have in mind, is figure out something like what sort of reward structure is going to mimic in this system an actual potential energy that would lead to some sort of cosmological evolution. How to actually do that, how to take a potential energy that is physically well motivated and map it onto a reward structure such that the agent learns to follow that trajectory, is a very interesting problem, but not something that I know how to do currently.
Okay, if there are no more questions, no, Andres.
So just to understand the last conclusion properly, does the fact that you can get it up to 100 steps means that the weakly coupled things are less rare than you might have expected?
So, right. So all of this, the probabilities are still going to be lower than the ones that we have in the theorem. But yes, if you did the random walk, you might be led erroneously to conclude that you can only ever add 2 or 3 things, right? And that would be wrong because we now know solutions where you can add 100 different sequences of blowups and have something that still allows for the possibility of a Sen limit.
One last question.
So if I understand it correctly, the number of choices at every given step of the agent is varying. So how exactly did you choose the observation space and the action space for your model?
Yeah, that's a very good question. So the action space was chosen. What we did was we computed all cone, comma, tree pairs that do not immediately force you into a case where there's not a Sen limit. Because if you were to add one of those, you would immediately be out of bounds, right? And it turns out that there's slightly under 1,000 of those pairs, and that was the action space. You are right that the second that you have added something elsewhere, that action is no longer available to you, and when you've added something, some of the previously available actions are not available. But these implementations actually allow for this. You specify the overall global action space, and the agent gets clever at how to make sure it doesn't. Basically, there's a flag that ensures that as you add more and more, that you don't do something that's disallowed. Yeah. And the observation space, basically it just comes from these trees. A state is represented by a sequence of 1s and 0s according to whether you've added a particular tree on a particular cone. And I should say that these slides aren't totally complete. My student at 4 a.m. sent me something, and we actually trained for another 40 million steps, and it actually starts to flatten out around 110,000. So we don't know what that means yet, but at some point it will stop learning, because this is not an infinite space, and you expect it to really flatten out and no longer uptick.
Okay, let's thank Jim again.
Thanks a lot.